I'm Professor Miller at BMCC, and I'm going to teach a little lesson about the binomial probability distribution and the normal approximation to the binomial. The website claims that 30% of its visitors click on an ad. So what is the probability that less than 2 of the next 10 visitors will click on an ad? So you would expect 30% of 10 is 3. You would expect 30% of 10, but I'm trying to find the probability that we have less than 2. You might want to start thinking about the relationship between the answer to part A and the answer to part B. Less than 20 of the next 100. The same proportion of visitors clicking on an ad, but a much larger number of people. So the binomial distribution is used in situations where you have repeated trials of an experiment. Repeated independent trials is the assumption. What you need to know to solve a binomial problem is the number of trials, that's n. For part A, that's 10 visitors to the site. Pi, what's pi? It's the Greek letter P. It stands for the probability. P stands for probability of success. It's indicated. So for this company, it's clicking on an ad as a success. And they expect a probability of, they expect 30% of the visitors to click on an ad. Notice that this isn't the probability that we're trying to find in the problem as a whole. It's just the probability of success on an individual trial. Every time a visitor comes on, we think there's a 30% chance that that visitor will click on an ad. X is the number of successes. Here you have to go slowly. What is the probability that less than 2 of the next visitors will click on an ad? So we don't want 2. Less than 2. Could be 0 or 1. So the probability that x is less than 2 would be the probability that x equals 0 plus the probability that x equals 1. 0 or 1. And in probability, we can add those two. I'm going to show you how to use Excel to do this. I'm going to compute this probability using the binomial dist function. So n equals 10, pi equals 0.3, and I'm going to do it for both x equals 0 and for x equals 1. Binomial dist. As I type this, see, it shows me what I need. The number of successes. Number of n, that's the number of successes. 0. Then comes the number of trials, that's 10. Probability, that's the probability of success again. And then this final is either true or false for cumulative or just the probability of this individual value. Cumulative would give me the probability of a value and all the values below it as well, added together. So that's 0.028 is the probability that nobody would click. We would expect that to be small, given that there's a 30% chance for an individual. Again, binomial dist for 1 out of 10 with a probability of success of 0.3 and 0.121. So the probability of 0 was 0.028. Probability of 1 was 0.121. Adding those, 0.149, about a 14.9% chance. That's part A. Part B, of course, is quite similar. N is 100. Pi, 30% chance of success for each individual. X, go slowly, less than 20. 0, 1, 2, 3, 4, 5, 6, 7, let's see, not 20, up to 19. Okay, so I could do this in Excel with the individual probabilities. However, we're going to use the normal distribution. That is, if you look at all groups of 100 people coming on the site and take a look at how many of those 100 people click, record that over a long period of time, you would get a relatively bell-shaped distribution, right? You don't always get exactly what you expect. Sometimes fewer people or sometimes more people click than you would expect. Well, what would you expect? What you expect, the expected value is called the mean, and for the binomial distribution, the mean is n times pi. It makes sense. It's a formula that you don't really need to memorize. It makes sense. If 100 people go to the site, according to what the company told us, 30 of them are expected to click on an ad. Now we want the probability of 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, up to 19. We make a little adjustment here. Here we're using this continuous distribution to approximate the probability of these discrete values. No problem in here. I just shade in all the decimal values in between those whole numbers. A little adjustment ought to be made right here. If you think about it, I should go to 19.5 to include any decimal values that round down to 19. It's a little technicality, not a big deal. Now we have a pretty standard normal distribution problem. We also need the standard deviation, which is the square root of n times pi times 1 minus pi. So for this problem, n times pi, we did that already. That's 100 times 0.3. 1 minus pi, that's the probability of failure, that the person does not click. That was 30. 30 times 0.7 is 21. So square root of 21. We're going to need that to compute the z-score. Because now what we're going to do is find the z-score for this value. So let's go back into Excel. And the z-score, put that down here, equals 19.5, that's my x value, most important form in this course, minus the mean, the expected value, that's 30, divided by the standard deviation, square root of 21. Negative 2.29. And now find the area associated with that z-score. The way the norm's dist function works, it'll give us the area below that, which, looking at our picture, that was precisely what we're trying to find. .0109. Okay. So we need a z, which is x minus the mean over the standard deviation. We decided we'd use 19.5 minus the expected value over the square root of 21, negative 2.29. Put that in our diagram. If you think about it, the diagram is not really all that accurate because that z-score should be pretty far away from 0. It's only going to be a relatively small probability. And in fact, we computed that using the norm's dist, 0.0197. Much smaller than the answer to part A, but not like 1/10 of it. It's such a nice relationship. So the probability that x is less than 20 is 0.0109, about 1%. So, what could we assume then? If less than 20 out of 100 visitors click on a site, well, that probability is so small that if that were to happen, we wouldn't believe what the website told us anymore about the 30%. So this is real statistics. This is inferential statistics. There's some value that we're going to test. They told us to believe them. We believe, but we want to verify. So we go out and we have 100 people sampled. They go on the site, and if we found only 19 of them clicked, maybe the website would tell us, oh, but that's just bad luck. And we would say, no, this is such a small probability that we don't think it's luck. At this point, we don't think the 30% that you told us is true. That's today's lesson.